So there you go.
Okay. Hello, everyone. So my name is Nicholas Matsakis, and I work on the Rust programming language. I'm a member of the Rust core team, and I work on the compiler and some other things. And for those of you who haven't heard of Rust, I kind of wanted to summarize it as briefly and concisely as I could, so I got it down to 5 words. Safe, fast code that works, okay? And I'm going to go through each of those words and kind of show you what I mean by each of them, right? Because there's a lot in there. So let's start with safe. We hear the word safe used to mean a lot of different things. So I mean it in a sort of particular way. If you've ever written any C and C++ code, you'll be familiar with these kinds of bugs that I'm showing you here on the screen. These are like the nightmare of all C++ programmers, right? And it's because they're kind of hitting these 3 things that are really bad to have all together. First, they're really hard to find and understand what's wrong because they manifest in some error, but the actual cause is usually quite distant from that particular problem you're seeing. Secondly, they can have really severe consequences, like security vulnerabilities or just kind of arbitrary behavior on the part of your program. And finally, they're really common. It's almost impossible to write a significant amount of C and C++ code without bugs like these occurring fairly regularly, right? And at Mozilla, where I work, we make Firefox, and there's I don't know how many millions of lines of C++ code in there, and I can assure you it's full of these kinds of bugs, as is every other project of that size, right? Even though we run linters, even though we do all kinds of things to find those problems. So fuzzing and so on. So you might think, well, I think we kind of solved this already. We had this thing called a garbage collector. We've had it for a long time. They've been getting better and better. And it's true that a garbage collector kind of handles the first 3 problems here pretty well. It's kind of got the sequential code working well, as long as there's some runtime implications that may be a problem for you, but those can be tuned. But this last problem, data races, a garbage collector alone does nothing to really help you here. And if you've ever written a lot of Java code, especially multi-threaded Java code, you'll know what I'm talking about, right? You can still have all kinds of surprising and hard to understand behavior, even with the garbage collector. So what we're aiming to do with Rust is take a lot of this work that has gone on in academia, a lot of this excellent type system research, and apply it, and put it to use in preventing all of these sorts of bugs, but not through a runtime mechanism like a garbage collector, but through the type system, detecting and guaranteeing that you don't have these problems up front in order to get your code to compile, right? And it can be a bit of a hard sell, I have to tell you. When I talk to people and I say, hey, I want you to use this fancy type system, it's going to give you safety guarantees, a lot of times what they hear is kind of like your mom saying, or your parents, I should say, saying, eat your vegetables, right? It's like, I know it's good for me, but it's not really what I want. What I want to do is ship this thing tomorrow, and this is just getting in my way. That's not, however, how I see it, right? I see safety guarantees, they are spinach, but they're like Popeye spinach, right? They're the kind of thing that lets you take this code and actually make it work for real, right? And I'm going to give you some examples as we go of what I mean by this, how this playing out sort of in real life. But here's one example that came from sort of in the wild. I've actually had almost the same experience as this fellow. He works at Faraday, which is a company that uses Rust. And he was inserting some parallelism into his product, and it didn't compile, right? And you could see that as a drag, but it turned out it was because there was a subtle race condition that would have arisen, probably not right away, down the line, and instead he learned about it right away, and he was able to fix it, right? And so basically what it is when you're working with these safety guarantees, some portion of your brain that is dedicated to making sure those bugs don't happen gets to work on other things, right? And you don't have to worry as much about the maintenance problems of, well, if I do this really clever parallelization scheme, what's going to happen when I leave and 2 other programmers come and get hired and maybe they don't understand it and they start hacking on the system? Is it going to break then? Those kind of problems you don't have to worry about, because if they do that, the compiler will tell them. So, all right, that's safety. What about fast? Well, we all kind of know what fast means, right? And here again, I'm kind of aiming at some particular specific meanings. We would like to be able to support code that's comparable to C++ in terms of how fast you can make it go. And one of the things we really want to support is this C++ notion of a zero-cost abstraction. This is something that C++ does really well, and I think it's not so well understood outside of that community. It's basically the idea that you should be able to use high-level looking language features, and they should compile down to very efficient assembly, and they should do that without the need for heroic compiler optimizations. You shouldn't need like an escape analysis to figure out if you can use the stack or not. Right? You should be able to tell the compiler, I want you to allocate this on the stack, and it does it, and that's great. The problem is in C++, if you're wrong, you end up with a crash or something else, and that's where the safety guarantees come in, right? But we also mean stuff like not having a garbage collector, because despite all the work that's gone in, there are still a lot of problems around garbage collection in practice, especially in big servers or areas where memory is a problem. You can wind up consuming a lot more memory. You can wind up with surprising pauses when you don't want them, that sort of thing. So we'd like to find a way to not have those problems. And we'd also like to be able to manage other kinds of resources besides memory, like resources, sockets. We'll see some examples where we take advantage of that. And the nice thing is, once you don't have a mandatory garbage collector, actually Rust goes a little bit further. We don't really have any mandatory runtime at all. So you don't even need a memory allocator if you want to compile to some target that doesn't have malloc. It's kind of like C in that way, right? So all these projects where you would have thought you have to use C, we'd like you to be able to use Rust. So if you have a big Java project, a big Ruby project, and you want to take some of that code and convert it into, say, Rust code and then plug it into the Ruby VM, that's okay, right? We can do that. So here's an example of that. This is some Ruby code that is used to test if a string is whitespace. This was in the, I don't know if it's still there, but it was at some time the actual definition of that method in Ruby. It uses a regular expression. As you can imagine, it's not all that fast. It's okay. You know, how often do you check if a string is whitespace? Well, it turns out if you're running Ruby on Rails, you check that a lot, like every time that a request comes in, because you want to look at the URL. And so some enterprising programmers said, well, you know what we can do? We could rewrite that in C. That's fine. And so this is what it looks like. It's a little longer. It's got some, if you look closely, you'll see it has a lot of Unicode assumptions baked in. There's also some raw C pointers running around, and I think it's correct as far as I know, but it could easily be wrong, and it could easily have devastating consequences in that case. But let's assume it's correct. So when they do this, Sam Saffron did this. By the way, if you run Ruby on Rails, you should use that gem. I understand it's good because it goes about 10x faster, this function, right? And then that takes it out of your Ruby on Rails profile. Well, he also later rewrote it in Rust. So that was what we saw before. He rewrote it, and this is the Rust version, right? And you can see it's quite a bit nicer than the C one. Actually, I think this was his prototype. He was expecting to make it longer and bigger. This was just the let's just get it working version. It uses a lot of high-level stuff like the slice, which is like an array with bounds checking, an iterator over all the characters in that slice, a closure that tests if it's white space. But it all compiles down to, thanks to zero-cost abstractions, the same kind of code you saw in C, right? So it runs the same performance. And that's the kind of thing we want to show. And we can go further than that. Is white space, we could build higher level abstractions. Like I'll talk a little bit about, we're at a multi-core conference, our parallel iterators that do the same thing, but they would distribute it over your cores using a work-stealing runtime, et cetera, et cetera. And I should mention, if you've written C and C++ code, especially if you've used auto tools, you'll be glad to know we make it really easy to take advantage of other people's libraries. So like all these abstractions are great, but if you have to download and run a bunch of stuff and hope that it compiles, not so convenient. It's much nicer if you can just add a few lines and have the package manager download it for you and all that stuff. We do that too. Okay, so that was fast. Let's talk about works real fast, and then I'll get to the heart of the talk. So I mean, kind of a pun here, I guess. Works, I mean both that people use it at work. So there are like 100 companies or so now on our Friends of Rust page, which is some subset of the people actually using it. I don't take the time to scroll too slow. You can go look for yourself if you want. But there's a lot of names you'll know on there, Mozilla, Dropbox, NPM. And I also mean that Rust has that quality, which I think it shares with a lot of functional languages and other languages, that once you get things to compile, they tend to work in practice a lot better than what you may be used to in other languages, right? And I think that's because they encourage you to be bulletproof, basically. They make you handle a lot of cases. And the end result is that your code actually works when those cases inevitably come up in practice, right? So this quote is from the NPM CTO, and she said, "I like Rust because it's boring." And what she meant was, whenever her pager goes off because some service is down, it's not the one that was written in Rust, right? It's usually a different one. And so put all that together, and I think what we kind of offer and what we want Rust to be is a sort of enabling technology. So if you use C and C++ already, we think Rust can help you do more than what you're able to do today, right? Because you can take energy and do more aggressive designs and not worry as much about maintenance costs and all that stuff. If you don't, Rust may give you another window, a way to go from Ruby to something that's faster, to eliminate a hotspot, use more parallelism, and so on, right? And part of that is we try really hard to foster a kind of open and welcoming community with, especially with a lot of education and opportunities to learn and so forth. So you can come hang out, ask us questions. We'd love to answer them. All right, so this is what I'm going to cover in this talk. I'm going to go through I'm going to start with these concepts of ownership and borrowing. These are the things that make Rust sort of tick, how we get those safety guarantees. And then I'm going to use those and show you how we can use them to do a lot of different parallel abstractions, like everything from shared memory with locks to sending data over channels and so forth, all without any data races. I'll talk a little bit about unsafe Rust and show what happens when you need to go past those rules and how can we handle that. And then some of our experiences using it at Mozilla and so on. So let's talk about ownership first. One of the surprises that came along the way from working on Rust is the way we handle parallelism. At first, we thought there's only one example of a language that lets you write parallel code that's not horribly bad, and that's Erlang. So we should clearly adopt the Erlang model 100%. We were going to have separate tasks with separate memory spaces, and that was the way we were going to go. But what we found over time was that actually the kind of threads plus shared memory model wasn't as bad as we thought, in short. It could be made to work, and we can model the rest of the stuff on top of that we wanted. And the way that that kind of came about, well, we didn't expect that, right? I mean, we have a lot of bad experience, as this sign shows. This is a Mozilla distinguished engineer, very smart fellow. He has this sign in his office, right? It says you have to be this tall, like taller than anybody else to handle multi-threaded code. And that was kind of what we assumed also. But if you look more closely, you see that there is a way to prevent data races, actually, right? So the reason that multi-threaded code is so painful is these data race conditions where you have many threads accessing the same memory and mutating it, right? And this is the kind of the definition of a data race. You have to have these three ingredients. More than one thread accessing the same memory, that's the sharing. One of those threads at least has to be mutating it, that's the mutation. And they have to not be ordered with respect to one another. So no locks, no condition variables. And usually the way you can eliminate data races most easily then is just take one of these three things out, right? You could go to sequential programming and say everything is ordered, but that's kind of not so good. It's not what we wanted. You could eliminate all mutation, and you have up with a functional language, which has a lot of advantages, but also some performance disadvantages. Or you can eliminate all sharing, and that's kind of this actor model I was talking about in the beginning. And that's great, except sometimes you do need to coordinate. Sometimes you have your shared database or whatever else and these values, and so we'd like to be able to handle those cases too, right? So what we try in Rust is a slightly different approach. Instead of just taking one of these ingredients all the way out, we say, we're not going to allow you to have sharing and mutation at the same time, right? It's okay to be mutating as long as there's only one reference to the data. And it's okay to be sharing as long as nobody's changing it. The problem is when you have more than one reference and those references are being changed. That's when you get surprises. And in fact, even that's a little too strong. So when we'll see that we have some kind of escape hatches where you can share and have mutable state, but you have to do it via some API that guarantees ordering. So a mutex is a classic example. And if you have a mutex, you want to have a lock, you want to have some locked data, that's fine as long as you're sure and guarantee that you actually use the lock correctly. Okay, so let's talk about the sharing and mutation thing. The way that we prevent you from doing sharing and mutation at the same time is through this system called ownership and borrowing. The idea is that you'll use data in Rust in kind of one of three ways. The main way is ownership. This is sort of the default. And you're familiar with ownership, I think, from your daily life, probably. So if you have like a book, let's say, that you own, and that book is on your bookshelf, that's your book. Nobody else gets to use it. And if they want to, they have to come ask you permission. But one of the things you can do with this book is you can give it to a friend and say, hey, happy birthday. Here's my introduction to CS or whatever books you own. That's my bookshelf. I don't know. And at that point, it's not your book anymore, right? It belongs to this friend. They can do whatever they want with it, and you have nothing more to say. That's pretty much how a data structure works in Rust. So here's some Rust code. It's the first we've seen, so I'll explain it a little bit. We have two functions, the main on the left and publish on the right. And we're creating in this first line where the arrow is, we're making a local variable. And what we're doing is we're taking a vector, so vec new. New is not a keyword, it's just a method in Rust, but it creates an instance of a type by convention and returns it. So we're going to make a vector and store it in the local variable book. And so what we'll end up with is this. Now, like in C++, this variable, its fields are stored on the stack by default. So this will be stored on the stack. And you notice I declared the variable as immutable. That's what the mute keyword means. So in Rust, if you just declare a local variable without any mute, then you're not allowed to make changes to it. We ask you to highlight the places where you're going to be doing mutation. That helps later on when you're reading the code. You can sort of see, oh, I see this variable is being incremented, this one is not. Makes it easier. And in this case, what we're going to do, the mutations we're going to do is we're going to push onto the vector. So that means we're going to add things at the end, right? And this works just like a vector in C++ or Java. You have some backing buffer. It gets allocated. It goes on the heap. It grows when it gets too big, that sort of thing. So in this case, let's say we're pushing strings. Then we'll have two strings. The fields of the strings are laid out in line. That's not too important. I'm not going to dwell on that too much. But the memory layout is very concise, right? Or it doesn't have indirections in it. OK. So next thing I'm going to do is call this publish function. And this is where things start to be a little more different than what you might expect. Because publish takes as its argument a vec of string, right? And what that means in Rust is that publish takes ownership of a vector of strings. So just like when I gave the book to my friend, when I give the book to publish, it's no longer mine anymore. So what's going to happen at runtime, when we do this function call and we give ownership of the book away, we're going to copy over the fields that were on the stack into the callee's stack frame. And then we're just going to kind of forget about our own copy as if we don't have it. Right. Now the callee can execute, publish, and it owns this book. So when it starts executing, it knows that nobody else in the whole program has access to this book but itself, right? Only through this local variable. It can do whatever it wants, and when it returns, at that point, nobody else has access to the book. Publish is done using it, so we just free it, run the destructor, and free all the memory. And so basically, when a function returns anything that it owns, which it hasn't already given away, gets dropped. That's what we call it. And that means you run the destructor, you free the memory, and you guaranteed, basically, that it's going to happen right here when this function returns, not sometime later. Right? Now, what would happen, now that we've come back to the main function, you might wonder, well, what happens if, after giving the book away, I were to try to use it again? And the answer is that you'll get a compilation error, because the compiler is tracking what you initialized and what you gave away, and it won't let you use those values that you've already given away, or you might have given away if there was an if or some other conditional. And this is basically how memory management in Rust works, right? It's kind of manual, like malloc free and new delete, but it doesn't feel like malloc free and new delete, if you're familiar with those. It basically feels kind of invisible. It's kind of behind the scenes. When you create a value, it's yours. When you give it away, it's theirs. And the last one, freeze it. And now, just to kind of drill this in, I want to emphasize how different this model is from a garbage collected by default model. Right? So this is some Java code. It's kind of equivalent. And I'm not really picking on Java in particular here. This is, I think, pretty typical of this kind of area of GC by default languages, where you have, say, like I'm making a vector here in the first line. But when I call publish, what happens here is not that I give ownership of the vector. Right? What happens is actually kind of unclear in terms of who ought to be using the vector after this function call continues. What happens at runtime is I'm giving a reference. And so now we both have access to the same vector, and we are entangled. Any changes that publish makes will affect the code that comes later if they in main, and vice versa. Right? And so one consequence of that is that I can't, for example, when publish returns, we can't free this vector, because we don't know, the function publish just by itself doesn't know if its caller may still be using the vector or not, right? And likewise, when the function main is finished, it can't free the vector because it doesn't know what publish might have done with it. Maybe publish, started a thread that's using the vector now. So in that case, if we were to free it, that would be a problem. So instead, we have to wait and wait until the garbage collector sees it and executes, right? And why is that not doing stuff? There we go. Okay. So my point is not so much that garbage collectors are slow, but that just looking at these signatures, actually there's a lot of information not there. Right? If you just look at the signature of publish, you don't know what it's going to do with that vector. You don't know if it needs that vector to be immutable while it executes, or if it's okay if it's being mutated, say, by another thread. You don't know if it's going to start a thread. You have to read and understand the whole set of code before you can know these interactions. And that's really problematic. Okay, so that was ownership. Now, ownership is great, but it's not. A lot of times, like if I give a book to my friend, I might be giving it to them as a present, but I might also be saying, hey, why don't you just leaf through this book, read a couple chapters, and then give it back to me when you're done. Right? And it works the same way with data structures. A lot of times what we want to do is more like sharing. And so for that, in Rust, we call that borrowing, and we have two different versions of it. The most common one is this shared reference that we're going to see first, where you can have many different copies that all access the same memory, but none of them are able to mutate it. So there's our example, and I'm going to make a vector here. This is all the same as the first example, basically. But when I call this use function, we see that the type of the vector on use is not vec of int here, it's ampersand vec. So that means it's taking a reference to a vector in sort of operational terms, but in a higher level, it's borrowing the vector from its caller. It's just going to temporarily make use of it. It doesn't need ownership. And on the other side, we don't call vec by value. We use this ampersand expression to say we're going to lend out the vector and give it to use. So at runtime, that's going to make a pointer. And the function use can run along, and it can read and do whatever it needs to do from this vector. And when it's done, nothing gets freed. This is because use did not own the vector. It only borrowed it. So when it returns, it doesn't free things that it doesn't own. Right? And as a consequence of that, we still have the vector here when we come back, and we can go on using it some more. So we saw now how you can pass references around, but what I want to drill into a little more is how this immutability part works. So the thing is that mutability in Rust is not binary. It's not on or off all the time. It's more like depending on where in the program you are is whether or not you can, determines whether or not you can mutate a variable. Right, so when we start, we have this variable book and we declared it as mutable. And that means that initially, we own it, no one else has access to it, we're free to mutate it. Right? So we can, for example, here we can call push. That's okay. But at some point, when we do this borrowing, when we have one of these ampersand expressions, now we start to borrow the book. And what we'll do then is we'll look and see what part of the code uses this reference. Right? So it basically extends from the point where you borrow it to the last place where that reference might be used. And in some cases, the reference might get copied into other variables or something, but here it's relatively simple. It's the last place that R is used. And I should add, this is actually using if you use, the current Rust compiler is a little stricter than this, same basic idea. This is the new version that we're going to be releasing soon with some of the newer, more ergonomic features that I'm showing you here, but it's the same ideas. And so during this period of time, while this reference is in use, we now actually have sharing. We have two different ways to name the same data. We can go through the original variable, book, or we can go through this reference R, and they both access the same underlying vector. And so for that reason, we're not going to allow mutation. Right, so it's okay to call like book.len. That just reads the length of the vector. That doesn't mutate anything. That's allowed. But if we try to call push, whether it be through the original variable book or through the reference, that is going to create an error, right? And the compiler won't allow it. So in this way, we guarantee that while the data is shared, while the reference is in use, you can't be mutating it, either through the new reference or the original path. Right? But afterwards, once the sharing is done, the variable returns to its original state. right? And we can mutate it if we like. So you have this notion of time, basically. Where in the program are you? Is the variable borrowed at this point? If so, you can't mutate it. All right, so that's shared references. And then I'll cover the last point, which is mutable references. So this is the same basic idea. You want to temporarily give access to your data structure, but you want to allow the function you're calling or whatever to make changes to the data structure. Right? So we have a function like edit that's going to change the book in some way. And it kind of looks the same syntactically. Instead of ampersand vec, we have ampersand mute vec to make the mutation explicit. But otherwise, it's kind of very similar, right? And in fact, at runtime, it's identical. We're going to pass a pointer, that's all. But what happens semantically is a little different. We'll make this reference, but the original variable, book, instead of making it read-only, we're going to make it completely inaccessible. You can't access it for any reason until the sharing is done. So if we go back to, well, okay. So then the edit function can execute and read the book, right? Now if we go back to this, this kind of similar example here, I've got the different lines of code. We'll see how it plays out, right? So the variable book starts out as mutable, same as before. But when I make the shared borrow, right here, we will again analyze how long is this reference in use. And in that period, we're just not going to allow access to the book variable. So here, the book variable, if we try to use it, we'll just get an error, even if all we're doing is reading from it, right? And this will be important for parallel access later. But we can use this reference R to do mutations or reads, as we choose. And afterwards, once the sharing is done, we can do whatever we want through the book, right? We're completely free. It's accessible like before. All right, so that's ownership and borrowing. That's the 3 patterns of Rust. But I wanted to show you just 2 other minor things which kind of elaborate this idea and show you how they play out, because you'll need it to see the examples of parallel programming later. The first one is what closures, a little bit about closures in Rust. So a closure is a callback. It's a function. It's basically a function that you define locally, which is allowed to reference the local variables from its environment and do things with them, right? And one of the things it can sometimes do is modify them. So here's an example where we have a counter, which is an integer variable. It'll be stored on our stack. And we're going to make a closure, that's here, that's going to increment that counter every time you call it. So in Rust, a closure is indicated by these pipes. In between them usually goes a list of arguments. In this case, we don't have any arguments. It's kind of like Ruby, sort of, if you've used Ruby. And the key idea is it's going to access and increment this counter in the parent's stack frame, right, directly where it's stored. So in a way, it's actually borrowing the counter. It has a mutable reference inside, that's how we implement it, to the counter on the parent stack frame. So in the same way that when you did a mutable borrow, we looked and saw where was this borrow used, when you create a closure that captures a variable, we'll do a similar analysis. We'll say, where is this closure used? And we're going to consider the variable to be borrowed for that duration. So now when we can, as long as we can still use the closure, that's fine. But if we were to try to access this variable that's captured by the closure, this mutably captured, I should say, that's not going to be allowed, right? And once we're done using the closure, then in the same way, the variable, the borrow ends, the variable returns to its original state. Okay. And in all of the examples I've done so far, we've been talking about all within one function, right? So you might wonder what happens when I go across and you have 2 functions. Say I call a function and it does some borrows and returns to me some new state. In that case, so in general, the Rust philosophy is that you don't have to write types inside your functions, but at function signatures, we do require you to annotate your types. And that helps to make our compiler tractable. It also helps to make the code readable. If you've ever tried to read a really long program with no type annotations anywhere, it can be a little confusing. And so we do the same. We ask you to annotate your borrowing patterns in the same way in function signatures. So now I'm showing you a little more Rust here. This is actually defining a method. It's a method that's in the standard library. So let me walk you through it. the first part is this keyword impl. That stands for implement, and it's a way to add methods to types. So here we're implementing methods, and the type we're implementing them on is this bracket t bracket, which is an array. So we're basically saying some number of t's in memory, adjacent in memory. It's a bounds checked array, I should say, or we call it a slice. So, and this is the name of the method, split at mute. And what this method does is it takes in a slice, that's the self, takes in a mutable reference to a slice, really, which means that it has like a kind of reference to the start and a length, and you can access any of the things in the array. And it takes a midpoint, which is an integer, and it divides the slice in two and gives you back two subslices before and after the midpoint. So I'll show you by example. This is a caller. This is an example of calling that method right here. And you see that we're calling it on vec with this midpoint of 3. So we're going to return a tuple, two values put together, and we can take them apart and pull out the less and greater halves. And so what we get back is something kind of like this. We have everything 0, 1, and 2, and then 3 and above, right? And it might look like, if I just show you this picture, I'm violating my mutable reference rules, because now I have less and greater, and they're mutable references to some memory, and also vec, which overlaps with both of them. And I'm only supposed to have one mutable reference at a time to any given memory, right? But that's where these tick A annotations come in. So when you're returning references out of a function, you can essentially tag with this tick A where they came from. And in fact, this annotation wouldn't be required. We have defaulting rules that would cover this case, but to make it clearer, I wrote them in. So what it's saying is, these two slices that I return were borrowed from the input slice. They alias, they kind of share same memory as the input slice. So that means while you have access to those two slices, you have to consider the input slice to be borrowed. So while we're using less and greater in this code, we can't use the original vec. Once we're done, we can use it again. Same idea. All right. So you've just learned Rust, or the subset of Rust that I'm going to teach to you today. But those are the key ideas of these ownership and borrowing, and basically this pattern just plays out across Rust code. But what's really interesting about it is what we can do with it, and in particular the parallel abstractions that we can handle. So the basic thing that we observed, if you have shared memory and shared mutable state, it's a really great foundation for implementing parallel abstractions. That's kind of, in a sense, the easy part. But what it is not very good at is ensuring that people use them correctly, right? You can give people a wonderful API that makes parallel programming really easy as long as they use it right. But if they make even the slightest mistake, they get into trouble. And so this is an example from Go. I'm not really picking on Go. It's pretty typical for any language that has shared mutable state, I would say, except for Rust. Just saying. No, not only Rust. Other languages too. So anyway, so here's what's happening. I'm making a mutable map, and I'm sending it over a channel. And what happens is I'm supposed to stop using the map at this point. Right? I just sent it to another Go routine. The other Go routine is supposed to read it and do whatever it wants with it. And all I'm supposed to do is just forget about it. But there's nothing that actually stops me from doing that, right? And I think the Go answer here is to run a dynamic data race detector, which I'm sure would certainly in this case trivially find this example. But in general, dynamic testing, is a good solution, but it also requires you to have a comprehensive test suite and so forth. And seems less good than if you can guarantee statically that you don't have the problem, right? So what we do in Rust is a little bit different. This is the same code translated. It creates a hash map, it inserts it, it sends it over the channel. But when you look at the definition of the channel, here's the send method on channels. You see, first of all, this is a method. It's defined generically over a channel of some type T. That's the kind of data that goes over the channel. And the key part is here. This parameter is going to take ownership of that data. Right? So when the function starts to execute, at the moment in which you've sent the data through the channel, or just about to send the data through the channel, you know that there are no other aliases to that data. And so then you don't have to worry about, for example, if the original function were to go and try to use that map again, it's not allowed to because it's been given away at this point. Right? So if you have ownership, message passing at least is kind of very nicely expressed, right? But we can go a little bit further, and we can do some other kind of patterns as well. And these are going to leverage the ownership and borrowing system to make these different APIs safe. So locking is a good example. A lock is a kind of, it's not hard to know how to use a lock in the abstract. If someone tells you, okay, you have a lock, anytime you touch this data, you have to acquire the lock. That sounds easy, but it's very easy to forget to acquire the lock, or it's pretty easy to release it a little too early before you were really done. And so what we do in Rust is we use ownership and borrowing to make sure that doesn't happen, right? So we have a type called mutex, and the key idea is this is not just a lock by itself, it's a lock paired together with the data that it protects. So in this case, it's an integer. So what we'd have here is a mutex with a shared reference over to this lock, and inside the lock is this data, and the idea is because the lock owns the data, nobody can get to that data without going through the APIs that the mutex or the lock offers. And really it only offers one method, which is called lock. And what that method does is it acquires the lock, first of all, so that'll block until all the other threads have, or until you have unique access. And then it returns a guard. And a guard is kind of, is another part of the mutex API. It overloads the deref operator in Rust terms, but it kind of acts like a pointer. So it has a pointer directly into this memory, and it lets you access it. So for example, we can do start guard plus equals 1, and that will increment this integer. But it also has a custom destructor. And when that destructor runs, what happens is it has the side effect of releasing this lock and letting people access it, right? So it's kind of a nice setup, because if you try to use, you can't get access to the data without getting the lock, and once you have access to the data, you keep it until you're done using it, at which point it naturally gets freed. So this is an example of using ownership and borrowing to manage other kinds of resources, in a sense. In this sense, the resource is the lock state, but the same techniques that manage memory, the destructors that free memory, also can be used here. All right, so that's locking. The last one I'm going to show you is fork join, which is a way to kind of divide up data and access it. It's kind of data, people call it data parallelism sometimes, but divide up data into discrete parts and process those parts independently. So there's nothing in the Rust standard library that supports that style of programming, but there are third-party packages that do. This is one called Rayon, which I wrote the first version of, but now it's maintained by a lot of people. And it consists of a bunch of APIs, but this is the core one, the most simple one. It's basically a method called join that takes two closures. And what it does is, conceptually anyway, it starts two threads, executes those closures, and waits for them to finish, and then it returns. So you kind of have this execution like, so diamond shape. And this is really handy for sort of divide and conquer style things, where you want to take some big set of data, divide it up into little parts, process them recursively down the line, right? So something like qsort. If you don't remember qsort, it's not that important, but this is sort of a qsort implementation. And the way it works, it takes in a mutable reference to some data, right? So we saw these before. This is a slice. And the key point is when qsort starts executing, it doesn't own the slice, but it still has unique access to it. Nobody else can be accessing this slice while qsort executes. Then it picks a pivot and does the partition. Like I said, if you don't remember how qsort works, not so important. Basically, it's dividing up the data on the left and right. And this is the key port. Then it calls split at mute, which is going to divide the data into two parts about this pivot. And then we're going to recursively process the data, right? And if you recall, when I call split at mute now, while I'm using less and greater, I've lost access to the original slice until they're done. And this recursive step, though, here we're processing two disjoint parts of the array. It would be nice if we could do this in parallel. And that's exactly what Rayon join lets us do, right? So we can call join like so. And now we process the less and the greater halves in parallel with one another and wait for them to finish. And the type checker is pretty happy because each of these closures is referencing a different variable, where one is referencing less and one is referencing greater. And in this case, it's a mutable reference. They have to be different. right? So this is another example where these kind of APIs are available in a lot of languages. Java has this awesome fork join pool. Scala has great parallel iterators and so forth. But they all could be misused, right? It would be possible to, for example, accidentally use the same slice in both halves. And every time I put this up, I think that is the most artificial bug. Nobody would do that. But in fact, I've made this bug like a number of times since I made this slide. It's really easy to do when you're copy and pasting and so on. And of course, if we try to do that in Rust, we get a compilation error because we only allow one mutable reference at a time. Each of these closures is now taking a mutable reference to the same variable. Yeah.
And again, I happen to be holding the microphone, so I'll use that. But this is sort of assuming that split at mute is doing the right thing and that it's not returning overlapping arrays or overlapping slices.
Yes,
is this done by some compiler magic, or are we trusting that library?
That's a good question. The answer is we're trusting it. I'm going to show you how that works out. But yeah, we don't, that particular function we do trust. But it is part of the standard library. The basic assumption is whenever you have two variables that are both accessible at the same time, they must be disjoint. And the Rust type system guarantees that. We'll see later you have escape hatches that let you write things that it wouldn't allow. And if you fail to uphold that guarantee, then yes, that's a problem. So using that, we've seen fork join. There's a whole lot of cool other things you can do. I mean, it's not that surprising in a sense. We offer basically threads and mutable state, which is the building blocks for all these different kinds of abstractions. And it's nice to see, you can see how they all play out with ownership and borrowing if you dig in. So getting at exactly this other question though, what about split at mute and how does that work? So Rust has this notion of unsafe Rust, right? And our vision here is that we want it to have an extensible language. We want to have a language with a relatively simple core that lets you write libraries that do any crazy thing that you could imagine, right? And there's lots of stuff that ownership and borrowing can't directly express. So we saw mutexes. I have this fork join that's work stealing. I guess I didn't say it was work stealing, but the QSOR implementation uses a work stealing thread pool under the covers and so on. Even just accessing a file, all these things are kind of outside of the core language. And what we want to do is allow you to write that code, much as you would in C and C++, but at the API boundary, use ownership and borrowing to guarantee that your callers are not misusing it, right? And so the core idea is this is a safe, what we call a safe abstraction. So we have this keyword, unsafe. It basically says, hey, trust me, I got this, and it gives you access to a couple of extra features that you don't normally get to use in Rust, a sort of superset of Rust, which is effectively C in Rust syntax. Right? You get raw pointers in particular. And the idea isn't that you like sprinkle this wherever you're having a problem, you just turn off the safety checks. The idea is that you write a boundary around it that has a safe interface, right? And I think I would say pretty much every language has this escape hatch somewhere. Sometimes they call it an FFI, where they call C code, but it happens at some point, right? You have to have some place where you kind of drop down to the next level. Even C has inline assembly, right? We have that too, but not surprisingly. And so we have it here, and by putting it in the language, that has this convenience that you can actually write things, in Rust all the way down. Like that's key to being a plausible replacement for C, I would say. So you might be curious how much unsafe code happens in practice. I know I was. And the answer is really it depends, right, on what you're doing. A lot of programs, none at all, but some have more. So this is a little mini study we did. I'm going to talk in more detail about it, but we were looking at this parallel CSS renderer that we used, that we implemented. It's now shipping in Firefox. And we wanted to know how much unsafe code was in there. And the first measurement we took, I have to say, was a little distressing to me, because it was 35% measured in terms of lines of code. And I thought, that is way too high. That's ridiculous. It turns out that if you look at the code, it's actually, you can kind of split it into two parts. First, there's the real code, the interesting stuff. And then there's all these auto-generated FFI bindings. Because as I'm going to talk about in a bit, this Rust code interacts with a bunch of C++ code and shares data structures with them. And these bindings, we're pretty sure they're correct. They get auto-generated. They get tested with a variety of test suites that are also auto-generated, and so on. But they're all unsafe, right? They're basically assertions telling the Rust compiler, here's the layout of this data structure that you're going to use. There's no way for us to know if it's correct or not. So if you look only at the interesting stuff, then you see it's 1.9%. So they have a few, basically they have a few parallel abstractions that they're using that they had to implement. And I thought that was a much better number, much more in line with what I expected. So there's nothing wrong with unsafe code, right? It's a key part of Rust in our mind because it helps keep the rest of the language simple, but it should be used well and judiciously, let's say. So along those lines, I wanted to spend a little time talking about how Rust can be used in practice and what it's like, our experiences using it in Firefox. And what we did with Rust here, so we've been, from the beginning in developing Rust, we at Mozilla have also been working on another project called Servo, which is a kind of re-implementation of the browser from the ground up, imagining what it's like, what would we do if we were going to do layout in parallel, how would it work, and so on. And what Servo managed to do is take just a little piece of that and deploy it now in Firefox itself, right? And the key part that we did was called CSS styling. So if you're familiar with HTML, or if you're not, I should say, basically the way your websites work is you have this DOM, which is a tree saying like, here's a paragraph of text, here's an image, and so forth. And they have a bunch of properties like what color is it, where is it on the screen. And these properties get computed via a set of rules called CSS. And the important part of this is that for any given node, the rules that apply just depend on its ancestors. So if you have a single node, you can trivially process all of its children in parallel. They should be independent from one another. So this is sort of embarrassingly parallel. And this is not escape notice. If you look, there's a Bugzilla bug reported 7 years ago saying, hey, let's parallelize this. That would be cool. And if you read the history of this bug, you'll see that they tried, I think twice, but at least once, pretty hard and failed, right? And I talked to the people who did it. It's not that it's impossible. It's definitely possible. It's just that getting all the data races out was a real challenge. And as fast as they could pull them out, other patches would land that would put new ones back in. So keeping the data races out was also a challenge. Plus they hit some annoying problems around C++ and Windows and so forth. Rust has a pretty good cross-platform story, I should point out here. And so basically it was an example of something we wanted to do. We had a team full of really good C++ people trying to do it, and they couldn't do it, right? And so we get back to Popeye here. So when you change the equation and you have the ability to use a language that does these safety checks, the results were different, right? In Rust, they were able to make it work, and in such a way that if future patches land that violate the safety guarantees, then the build breaks, and so somebody notices. So that's pretty cool. It works. Unfortunately, I don't have a lot of measurements. I keep bugging the team to send me more. These are the ones I have. They're pretty good in a sense. So what I have to explain is that these are measurements from the moment the browser starts executing until you see stuff on your screen. And it includes a lot of things. And only a little part of that is the page layout, and only a part of that page layout is the CSS styling, so the part we actually optimized, right? But you can see that there was nonetheless a pretty dramatic effect for some pages. Other pages, not as much, but definitely a big win, especially in browser terms, where it's pretty hard to score improvements on these pipelines. And so the other part of this story that I think is really cool is that in terms of the whole browser engine, we ported the CSS styling into Rust, and we're doing another part now that'll land in a little while called web render. But all the other code stayed in C++. Right? That's what all this FFI code came from. So that means you don't have to adopt, if you want to adopt Rust, it doesn't have to be, I'm going to rewrite all my code and have a flag day where we like convert everything to Rust all at once. That's not very practical. You can do it piecemeal, a piece at a time, and compile a Rust to a library that links in with the rest of your code, whether it's in C++ or something else, right? All right, so I've kind of given you the hard sell, I would say, on the Rust type system, what I think it has to offer, and all that stuff. And I want to step back a little bit and talk about the Rust project, kind of as an open source project, how we do our governance, how you could get involved. The first thing is Rust, we have tried from the beginning to be a kind of independent open source project that is governed independently by its users, right? So we have a leadership structure where we have a lot of sub-teams. All the official decisions are made by these sub-teams, like what language features to add, what to prioritize. And right now there are about 60 people involved. There's some overlap between teams, so the numbers don't quite add up. But of those, only 10 of them are employed by Mozilla. So it's not a matter of Mozilla kind of completely controlling this endeavor, and we would like to see more companies getting heavily involved. A lot of those people are employed by other companies that are using Rust, of course. And one of our big things that we've been working on is basically how to manage the stability of Rust that we want, because people don't want to build on a ever-shifting language, while continuing to innovate and bring new features and make improvements. So in the early days, we basically just broke the world all the time, right? And a couple years ago, we declared a 1.0, and we have not been doing not been doing that ever since. And I can't tell you what a nice feeling it was to go back to a Rust code base after 6 months and build it and find, oh, it still builds. That's nice. But we still want to have these new features. And so the way we do this is we have different channels. We have a nightly compiler, which allows access to all the features of Rust, including ones that we're not sure about. It gets built every night. It's kind of like the browser pipeline. And if you use that one, you get to use everything, but you're taking on, if you use those new features that are not stable, you're taking on a certain measure of risk that they may change, and you may have to recompile your code and fix it. But you also can give us feedback, right, and control the direction of those features. And if that's not acceptable to you, we have a stable release that comes out every 6 weeks. It contains only those features that we are willing to commit to, and that will continue working forevermore, right? In terms of designing new features, we do that all through this RFC process. So people can come either internal to the team or from outside and suggest a feature by writing up an RFC, and then there will be a lot of comments and back and forth, and eventually we'll either accept it or not, at which point we start moving to the implementation phase. And I chose these ones, which are written by Josh Triplett, who works at Intel, and he's now part of the Lang team in some roles. But initially, when he wrote, especially the first RFC, he wasn't. Right? This was a feature that came from the outside, and that seemed like a good idea to add unions for FFI with C, and we worked through it that way. So these features come. Kind of the important thing I want to emphasize is everybody goes through the RFC process, whether they are internal to the team or not. Right? And it's been a really good thing for the product, I would say, well, for Rust. So at stepping up one higher level, we also have this roadmap process. So in terms of where RFCs decide about a particular feature, but our roadmap process is kind of every year, and we're about to start for 2019 or 18 coming up. We kind of set what are the overarching themes that we're going to be working on this year, and that kind of determines which RFCs we're most likely to accept, if they fit into those roadmap goals or not. All right, so I hope I've given you a taste for Rust. I think Rust is a pretty exciting thing, obviously, because I work on it. But if you're interested in Rust, you should come and talk to me, or you can check out one of these books. So the O'Reilly book, I think, is actually available now. I think I saw something about just in the last few days it started to ship. But there's also a book on our website called the Rust Programming Language. And I also have some screencasts that I made into rust.com that will kind of walk you through ownership and borrowing and all that sort of thing. So thank you very much. I'm ready for any questions.